Hello, thank you for attending this presentation. I'm going to talk about accelerating timing closure and physical planning. My name is Himanshu Bhatnagar. I'm a CEO of Excellicon, and Excellicon, as you know, is a company that started doing the developing products for timing closure, first of all in constraints, and then later on we moved into clock tree and flow planning. So we're going to give you a brief overview of all the products and how do we fit into the ASIC timing cycle. And then we're going to go a bit more in details about, when you are developing the timing constraints, what are the issues you're going to have and where do you spend most of the time? So we're going to go over the constraints, promotion, demotion, budgeting, and how does it help in the timing closure? We're also going to talk about the hierarchical SDC generation because, as you know, there's a lot of times when we are doing timing closure, we have to come up with different types of variations of SDCs. So we need to come up with a hierarchical SDC generation and how it can be done automatically. Then we're going to move on to the timing equivalency checking. This is a fairly new concept. But it's picking up momentum because there have been some silicon failures in this field. We are all aware of logical equivalency checking, but there's also a timing side of it which no one really cares about. And this is where the issue exists. So we'll talk about the timing equivalency checking. And then we're going to go over to the constraints verification and management feature of our products. If you already have the constraints, how do you validate it for correctness? Then we're going to go over to the clock tree. So the first five first three, constraints promotion, equivalency checking, and the constraints verification. These are in the constraint space. The clock tree analysis and verification, that is going to talk about the clock tree because clock tree is the heart of any silicon system. So how do you want to analyze the clock tree properly, and then you validate the clock tree so that you don't have incorrect clock tree implementation. And finally, we're going to talk about how to do the flow planning early at the RTL level even, and so that you don't have issues later on. So with that, let me go over the ASIC flow. So the ASIC flow, basically there are two parallel tracks which go on. First the front end, and then staggered slightly later on, the back end starts. In the front end, first bar shows design and integration. This is where you're going to be basically stitching the IPs, and integrating the top level and all that. And then follow that by you spend majority of the time in functional verification of the entire SOC. Now, in the parallel track, the implementation cycle starts. So staggered is the initial timing closure, although there's no such thing as initial timing closure and final timing closure, but I broke it down into two because initially there's a lot of time spent in developing the timing constraints, then you do synthesis, you do flow planning, and a lot of iterations keep on going back and forth, back and forth. When you're kind of in a good state, then you're going to be spending the rest of the time just fixing the setup and hold fixing and probably some ECOs before you tape it out. Between these two tracks, there's a lot of interaction goes on between the front end and the back end. And you're talking to the RTL engineers, finalizing the SDC, making sure that the timing captures the real intent of what the SOC is supposed to do. So and also when you're doing flow planning, you need generally the implementation, the backend folks don't really know the data flow, so they have to keep on talking to the front end folks, the architecture folks, to see how the data flow, how the clocks are supposed to basically go with the data flow, so that the clock topology along with the data flow, so the blocks they are placed near each other, they can meet timing easily. So this is where actually a lot of issues occur in between the initial timing closure and the top front end, and there's a lot of interaction which keeps on going on. So what are the challenges in the ASIC flow? As I mentioned before, it's a highly iterative and tedious process. You are going to go through a lot of iterations between the two parallel tracks, and a lot of discussion is involved. Then when you developing the constraints, now you are developing the constraints for, if you have a big SOC with multiple blocks and different modes, so you're going to have to develop constraints for each of the block and the different modes of operation, and then put it all together. That creates a huge management issue, because managing all these different timing constraints and then making sure they are correct, and then getting to the top level is a monumental task. It takes like months of work to get it, and even then most of the time you don't get it right. Today the building of the constraints for top level is done manually. And so we're going to show you a method of automatically promoting the constraints from the lower level. If you have an SDC for the lower level blocks, how do you promote it to the top level fairly quickly, and within a few minutes to maybe half an hour or something like that, for even a large SOC, so that you can get to the top level. As you know, once you get to the top level, it's very important you can enable other tasks like CDC or power analysis, all that thing very quickly. And then once you get to the top level, you can budget it to the lower level block for place and out purposes and all that. So that way you're going to reduce a lot of iterations also, because you're starting with a budgeted SDC. Now, the other thing is the design optimizations, when they are done through synthesis or place and route, like cloning, decloning, register optimization, they may actually invalidate some of the timing constraints. Some paths which you were targeting at the, let's say, the RTL stage, they may disappear when you after synthesis and all that. So how do you make sure that the gate level representation of the SDC is same as what the RTL representation? So that's where the timing equivalency checking comes in. Lastly, the gate level SIMs, we're going to briefly touch on that also. Why are they still being done? And I'll go over the details a bit later on that front here. And with our tools, basically, you can minimize the running of the gate level SIMs. Now, the next topic is a clock tree implementation. So clock tree implementation is, clocks are the heart of the system. It's very, very important to understand how the clocking is done in the entire chip, because you have a block level clocking, then majority of the clock interactions happens at the top level, and that's where the complexity happens. So how are you understanding the clock topology, how they're propagating, how they're interacting with each other? That takes a long time, and generally people use paper diagrams to understand how that thing is done before they even go forward with any of the other tasks. Secondly, clock tree, when you do implement the clock tree, you know that the clock tree is a majority of the power hog in your SOC is coming from your clock tree. Estimates are anywhere from 30% to 60% will come from a clock tree itself, how they have implemented. Yet there's no really a good tool to really understand whether the clock tree has been implemented correctly or not. If your timing is met, you're going to say, okay, my clock tree is fine. But that's really not the case. Timing can still be met, but the clock tree can be really not properly implemented and consuming a lot of power. So you need to pay a good attention to the clock tree itself, and if you want to reduce the power and other things. And lastly, the skew groups. Today, the skew groups are defined manually. Only when we have timing closure issues, then we start going into the skew groups. It may be better to really do the skew groups definition early, because not only it helps in the timing closure, but it also helps in the power. So we have a tool which can automatically generate the skew groups, and then you can use that for your backend. Lastly, the flow planning. So flow planning is when the RTL comes to you, to the implementation folks, right? How do you determine which blocks need to be grouped together for place and route and create a partition. That really comes from the understanding of how the data flow is and how do you want to partition the chip. So you have to talk to the architecture folks, and then you come up with the how do you want to partition the chip properly. So our tool would basically look at all the criterias and it will tell you what is the best way of partitioning the chip without changing the RTL. So basically you can do a what if analysis with multiple scenarios you can create, and you can do multiple partitioning scenarios and see what is the effect of this partition versus the other partition. After you've done that, you want to, how the blocks are interacting and all that information that can be gleaned from the scenario here. Last is secondly, the flow plan. Is it truly reflecting what is in the RTL? So if you have come up with the two partitions and you're going to abut it in the flow plan, and there's a glue logic present in the RTL, well, how would you know? So the tool will actually tell you that if you were to do abutment flow in the flow planning, then you can you're going to have these kind of issues. So there are many rules like this which will check the flow plan against the RTL and will update you right up front. Now, let's go back into the timing constraints. So in the timing constraint space, as you know, the SDC or tickle SDC or timing constraints, whatever you want to call it, it is at the heart of the system. Previously, it used to impact only the synthesis because that's what we used to do it, and then STA. Then the place and route engines came and they started doing the timing driven placement. Again, the seed input was SDC. Now, pretty much the entire tool chain, if you do static analysis, then you have to basically use SDC as seed input. So you're from your power analysis, from your clock domain crossing, from your clock tree synthesis, test and FPGA, everything is centered around SDC. So your SDC has to be perfect. You can't make a mistake because you are going to get incorrect results if your SDC is incorrect. Now, the problem is the early availability of SDC is not there. As I mentioned, right, you may have IP SDC, but you don't have top level SDC. And the other thing is the correct type of SDC may not be there. For the SDC which is used for clock tree synthesis is drastically different than what you use for static timing analysis or even for synthesis. So the type of SDCs meant for driving different implementation tasks is going to be different for all these different things. That, imagine now not only you have different modes, you have different blocks, but the types also is going to create a nightmare in managing all these different types of flavors of SDCs. And some of it, which I've listed here, single mode for, let's say, sign off, fastest clock propagating for synthesis. Then you have merge mode for maybe you can use it for place and out. You can do a full flat SDC for final sign off, hierarchical SDCs when you're still doing some blocks and closing timing on the other ones and all that. Okay, so in terms of products, what do we offer? So we have 4 different products. The first 2 are in the constraint space. So the constraints manager, or conman for short, is basically used to generate the SDC from scratch. So if you just have an RTL or gates, nothing else, no timing constraints, we only need a .lib if you have instantiated some cells in there, then the conman will discover all the clocks and all the related constraints and will generate the SDC for you. Okay, so this uses a formal technology and it discovers all the clocks and the control signals and pretty much all the constraints. Even it will synthesize your case analysis also, and the IO delays, set clock groups, which is clock relationships and all that, and will write out RTL for you. This tool is also used for promotion. So promotion, if you have already existing SDCs for your lower level blocks and you want to basically build the top level, then you can use that for promotion. Concert has got a lot of, that's the second product in the constraint space. It's a different tool because it uses different types of algorithms, there it does require your RTL or gates as input along with the SDC. Now this SDC is your own SDCs or manual or command generated SDCs, doesn't matter. And by the way, when I say SDC, I don't mean just SDC format. I mean tickle SDC. You know, you could have procedures, you could have for each in collection, all that sort of thing is completely supported. So Concert is a verification engine. You can use it to validate your kind of timing constraints. It uses formal and other types of algorithms also in order to reduce noise, and that's where we had really concentrated on in order to reduce or eliminate the noise completely. The Concert engine is also used for demotion and budgeting, as well as equivalency checking, false path and multi-cycle path verification, which is part of your exceptions toolbox, and lastly something called SI enablement. So I'm going to go through some of the topics here, but not all, because we don't have that much time. And then you can write out an incremental SDC along with the reports. Now, Contree, we're going to go in depth about it. That is about the clock tree. It has visualization, as well as you can basically understand how the clocks are propagating. A lot of debug capabilities are built in. It will also do CTS verification. These are rule-based CTS verification. They are independent of the STA type. Basically, it's looking for things like excessive buffering or the clock topology issues, routing issues, all that sort of thing. It will do that for you. It will also generate clock tree exceptions, implicit, explicit exceptions, as well as skew groups. Construct is our latest product which we introduced, and this will basically generate the different partitioning scenarios. You can also repartition the RTL SDC and modify a flow plan at the RTL level very early on, so that way you know what the sizes are, and then lastly you can validate the flow plan also. Okay. This is a kind of a laundry list of all the features, which I'm not going to go through. I've already described some of them, but since this presentation is going to be in the net, you can review it on your own side, on your own pace. Now let's go a bit more into the promotion, demotion, and budgeting. So as I mentioned, if you have IP SDCs available, or some of the blocks you may not have SDC at all, right? You can still promote it. The best thing is to promote it to the top level as soon as possible. So get your IP SDCs, get the top level as soon as possible. This will enable you to run other tasks like CDC analysis, power analysis, all that very quickly. Generally, if you do it manually, it will take months, but through the tool, you can do it in minutes and then get to the top level. And then you can follow that up by budgeting the SDC at the RTL level or the gate level. So with the budgeted SDC, now you have a good interface timing, and you're not going to go through ping pong iterations when you're doing final timing closure. So, and this can also be used to write out hierarchical SDC generation with fully budgeted as well as .lib generation. So entire flow is encompassed within the two tools. You use Conman to do the promotion, get to the top level as soon as possible, and then do the budgeting for your place and route blocks, and then you go forward with it as well. When you're doing a static timing analysis, use Concert, write out a .lib also for the different blocks, and then do the hierarchical SDC generation and time it. Now, in terms of budgeting, there are different methods which we provide. Now, we have fine grain, coarse grain, and manual, and then different percentage-based, logic levels-based, or delay-based. So percentage-based and logic levels-based, obviously, you can only use the RTL level here. The delay-based, well, all three can be used at the gate level also. So here, the delay-based, you can use SPEF or the SDF, and then do the budgeting. It will really reduce a lot of iterations. Now, in terms of the hierarchical SDC with the QTM, here is giving you an example. So let's say you have a top level here, and with some glue logic here, and this is U1 and U2 core. So simply, if you want to write out a SDC, hierarchical or budgeted SDC for U1 and U2, you simply do a demotion and budgeting to these two U1 and U2, and then write a hierarchical SDC for the top level with U1 and U2 as your blocks. If you want to write out SDC for U1 and U2, of course, just simply write it out U1 and U2. And then for .lib writing, you specify U1 and U2 and write out the .lib here. Now, let's go into the equivalency checking. This is actually a very major feature and it's picking up a lot of momentum. This is a new feature, so some folks may not know about this thing here. So this is where I'm going to explain to you. So all of you guys understand LEC. I think no one really tapes out a chip without running logical equivalency checking. The problem with the equivalence checking is it's only doing the functionality. It's only targeting the functionality. So if you have an RTL and you go through ASIC flow, and then you get the gates, you're going to run LEC to make sure that the gates functionality is same as the RTL. Well, what about the timing side, right? You may have an SDC, RTL SDC, which is targeting RTL. And then after your synthesis, you come up with the SDC. Now, some paths may have disappeared or appeared. Are you the same timing intent we use for RTL? Is it still valid for gates? And same thing for place and out. If the ASIC flow is basically your place and out also, well, pre-layout SDC and post-layout SDC, are they going to be capturing the same timing intent? Because you may go through cloning, decloning, register optimization, pin swapping. All sorts of things happen in these backend tools. So you have to make sure that the SDC is actually still capturing the same timing intent. And we have seen some chip failures on that. So it's very, very important to run the timing equivalency checking along with your LEC. And this is the example case, which I wanted to basically highlight with one of our customers. It happened. There was this CPU running at 800 megahertz and the NOC block running at 400 megahertz. And the path was going through this P1 here. Now, the guys put a sub-cycle path of 2 through this P1 here. After synthesis, this and this bubble got optimized, and basically they did the synthesis the full top level here. And the synthesis tool did a boundary optimization and punched this path through the red one as shown here. And they use the same SDC, which they use for RTL. Now, look at what happened. Previously, the registers, or only in the NOC block registers, were multi-cycle path of 2. But now here, because this is logic optimization, right, the CPU registers also got multi-cycled to 2, and this caused them a delay in the chip. They only found out in gate level SIPs here. So we do offer equivalency checking. The traditional equivalency checking is top to block. So you have a top level, you have a block, top level, and you have a block level here. You want to basically make sure that the IP SDC is in context of the top level SDC. So for example, if you do promotion, so you want to make sure that the IP SDC, which you did promote to the top level here, is in context of the top level. So this is the traditional equivalency checking. Has been around for a long time. The ones which I was talking about is top to top. Top to top is that we provide different flavors: 1D2S, 2D2S, or 2D1S. So 1D2S is design remains the same, SDC is changing. For example, as you're going through the timing closure flow, you may be adding false path, multi-cycle path, but your gate level netlist is constant. So you want to make sure the previous SDC is still capturing the same intent as the new SDC, with the exception of the additional false path and multi-cycle path which you added. The 2D2S and 2D1S are more interesting ones. This is because the design structure has changed now, because the design structure like synthesis will do some optimizations, or place and route will do some optimization, cloning, decloning, optimization, all that sort of thing. So think of it, this could be RTL and SDC, gates and SDC, or pre-layout and SDC, post-layout SDC, or you may have pre-ECO, post-ECO, and using the same SDC. So these are the different flavors which are used to check the equivalence checking. Let's go into the constraints verification features. In the constraints verification, this is pretty much in line with other tools also. We do check for pretty much everything. The difference is that is in the noise. We added 3 separate things. We use formal, we use CDC analysis, as well as constraint simulation to knock out all the different noise related issues. So you're going to get really the problematic areas only, and not the other ones here. And some of the things which I want to show you in the constraint simulation part is that for some of the constraints for which there is no way you can, static verification tool can identify the issues, we write out system verilog assertions. For example, false in timing intent, false in multi-cycle path, disable clock gating check or clock waveforms, right? If you have a clock waveform defined a programmable divider, how can a tool say is clock waveforms correct or not? So we do write out a system verilog assertions to cover those areas which cannot be validated by static tools here. This was a paper written by one of our customers. By using SVA, you can basically run this is a traditional flow here, which is gated by SDF, but you can basically do it very early on at the RTL stage. That way you reduce the gate level sims itself here. We also have some things on the Excel spreadsheet for clock management, where you can basically write out constraints and then take it into Excel spreadsheet where you can modify it to your heart's content and write out an SDC here. Now, quickly going over the clock tree analysis verification. As I said, clock tree is one of the important tools in the portfolio, and this is very, very important to analyze, to understand how the clock syncs are. It writes out skew groups. It will do the clock tree verification, even if your timing is not met. Lastly, you have a construct tool, which is a flow planner. As I mentioned before, it will do the partitioning scenario without changing the RTL. Then if you want to do the RTL changing, the tool will actually partition the RTL for you. It will also do a flow plan very early on, and at the RTL stage. That way you know what the area is and how the pads are going to be placed and all that thing. And finally, this is a new concept called verification of the flow plan. The issues which you find the flow plan at the later stage because of the RTL, and you say, I wish I had modified the RTL to fix this thing, is, for example, feed throughs and all that thing. You'll find out all these issues very early on so that you can correct it before you're going into the full really flow plan. So that's the end of my presentation. It's been a very short thing. So if you have any questions, please do let me know. Thank you.